Okay. I think I'll get started. Okay, what are we going to do today? I'm going to talk about some simple codes. I'm going to talk about the classical repetition code that you've already seen sort of on this slide about von Neumann. And I'm going to talk about amplitude damping code. And the reason I'm talking about these very simple codes is because they actually illustrate very general principles. And if you understand these general principles from these small examples, then you can apply them to more complicated code constructions. So I'm also going to talk about code concatenation and what's called the fault tolerance threshold theorem. So we'll just see how far we get. So in the last lecture, my language was a bit abstract for some of you, perhaps, because which is not entirely ideal if you want to understand something new, but it's because it's a general formalism, one has to be, abstract, because it applies to many physical situations. And I just want to give you two examples of, dynamics that one could look at, and dissipative dynamics that one could look at, and one could study what an error correction code would have as an effect. And so as I already discussed the thing that, if you characterize a single qubit with some basic parameters, you do that with a T1 and a T2 time, and assuming that your environment is at fairly low temperature, you expect to be, if you're in an excited state, the qubit is in the state 1, it will relax into the state 0 after some typical time T1, and the reverse process will not be very common. And so that's an example of an error which is not a Pauli error, because it's not a bit flip. There's no symmetry between 0 and 1. 1 goes to 0, but 0 does not go to 1, except if you have a somewhat higher temperature. Is there a stick here? Let's see. There's a stick there. So you could describe this by, again, some Lindblad-Master equation, because maybe this is how this comes about. And then you would have, you could model this by one quantum jump operator, which would have associated with it some rate kappa, and sigma minus is an error operator mapping 1 onto 0. And remembering what we said yesterday, from this we can construct also a Krauss. We can construct a superoperator. And for this superoperator, I would have for short times, I'd have two operation elements, two error operators, E0, which is just proportional to the sigma minus with the rate, and then there's some time scale in here, and E1, which is the sort of no decay operator. So you can say, well, I'd like to design a code, and this has been done, that satisfies or approximately satisfies the error correction conditions for these two error operators. And so I want to discuss the 4-qubit code, because then it leads to other codes, which indeed approximately corrects or satisfies the quantum error correction conditions for these two error operators. So what it means that if you're for short time scale, it's only an approximate, because if you do the analysis in details, it brings the error probability down from something like tau kappa to tau kappa squared. So it's not something that brings the error probability down to 0. So the idea is now you are undoing or trying to partially undo the relaxation of this atom or qubit, whatever you may call it. Now, one other situation that you may study, and I just want to point this out. So in these lectures, and sort of if you think about the theory of quantum error correction more generally, often we talk about encoding qubits into more qubits So 1 qubit into 3, etc. But there's also work which shows that you can try to encode a qubit in an oscillator or in a bosonic mode. For example, represented by a single cavity mode that you can isolate pretty well and that you could couple to via qubits for transmon qubits and things like that. And there's a lot of space in an oscillator, of course. So this is actually, I think, also quite interesting, and maybe I shouldn't advertise this, but my master students will give a talk about this at the presentation skills workshop. So you can listen to him if you find that interesting. But so typically, if you have a cavity mode and you want to write down a very simple model describing the dissipation, you'd say it is in contact with some finite temperature reservoir. And with that reservoir, we're going to associate two rates. One of there's a rate at which photons are added to this cavity mode, and there's a rate at which photons are leaving the cavity. And these should obey some detailed balance depending on the temperature of the reservoir. And again, you could extract from that, for example, if you're at t is 0, two error operators. And you could imagine, or you could look at possible code words in this oscillator mode and see how that subspace, that two-dimensional subspace of this infinite dimensional oscillator space protects against these error operators. And I think I make a few comments in my review about this. Anyway, I'm not going to go into codes that encode a qubit into an oscillator in this talk. Okay, so what I want to do now is to discuss a few very simple codes. So we'll start with the repetition codes, by which we can illustrate a surprising number of features that also are pertinent to the surface code. And then I'll also discuss the amplitude damping code, a 4-qubit code. And for the repetition code, what is nice, so who has worked on this Delft experiment? Is there anybody? Okay, yes, you've worked. Okay, so what is nice now that for the repetition code, I can actually point to 2 experimental papers, and I may say a few words about this, in which this code has been realized. Okay, so we'll come to that in a moment. Okay, so yes, so repetition code for 3 bits is completely trivial. So instead of having a single qubit, I have 3 qubits or 3 bits. And I call this the logical 0 and the logical 1. And this subspace obeys certain properties. For example, it's clear that the first, if I look at the parity for the first 2 bits, it's even, or the parity of the second 2 bits is even. And if I could also do this with m bits. So this is the 3-bit repetition code. Here I just have n bits. And so let me just write this up. So for 3 bits, if I ask myself for 3 bits, what are the states that obey the property that the parity of the first 2 bits is even, the parity of the second 2 bits is even, these are the only states that obey this property. No? So some people may ask themselves, if you're used to writing Pauli matrices like this, some people may ask themselves, why in quantum error correction do you always write Pauli matrices like this? Now, you can see already that it's just a convenient notation because we'd have double subscripts or other messy things. So if I talk about Pauli matrices, they're always y6, and so on, x5, meaning that this is a poly x acting on the 5th qubit of some code, and y6 is the poly y acting on the 6th qubit of some code. Okay. Okay, so these products of these are parity checks. They're just classical parity checks for a more general quantum code. There can also be parity checks which do something like this, which means that this is a string of Pauli matrices. It's an operator that has eigenvalues plus or minus 1. When I apply it to a state that has eigenvalue plus 1, then this parity check is satisfied. Sort of a generalized parity check. When it has eigenvalue minus 1, we say it's not satisfied. So I'm leading up now to introducing to you some terminology that pertains to stabilizer codes. Because we can see the repetition code as a very trivial example of a stabilizer code, and we'll come to sort of more formal definitions in a moment. Okay, so now if these were classical bits, one could, in order to do your error correction, you'd say, well, okay, perhaps some bit flips happen. If a single bit flip happened, it's clear that I know whether it came from 0 or 1. So if I just measure all the bits, I determine what error happened, I undo it. But this I cannot do if I have a quantum state, right, in general. I have some superposition. If I want to use this to protect quantum information, the general state would look like this. And I cannot individually measure, if I would start individually measuring every bit in the Z basis, I will find, whether errors happen, but I've also lost my information, right? Because at the end, I just have some, I just obtain some state like this. I determine it came from 1, 1, 1, but I've also measured my qubits, right? I don't have further information about alpha and beta. So this is the first departure from classical. I'm going to try to mention departures from classical error correction. Of course, this is very, very trivial classical error correction. But to build hardware, we don't need complicated quantum codes. We need maybe very simple codes. And the reason I'm doing that is that I want to make clear that there is a very good reason why I think we don't have a quantum computer yet, because quantum error correction and realizing quantum error correction is really a lot more complicated at many steps. Okay, so what we need to do. Okay, so let's say. Okay, so yesterday I discussed about the quantum error correction conditions. I said, what in that general formalism, what does error correction do? I have errors that send the code space to different orthogonal subspace, and I just need to know where I am. Yeah. Now I'm saying here the code space is determined by these check operators coming out to be +1. So I should measure these check operators. So I should measure the eigenvalue of this operator and that operator without measuring the eigenvalue of Z2 or Z3 individually. Yeah? So I have to set up some experiment. I mean, you can do this using 2-qubit gates. I'll show you the circuit in a moment, but I think it's also worthwhile to think about this a little bit more deeply, because this is the workhorse of quantum error correction. You don't need to do 2-qubit gates very well. You need to do parity check measurements very well. If you have a shortcut way to doing that, go ahead and do it. It's much better, perhaps, than doing it in some direct way. Because we need to make sure that the signal coming from the first qubit sort of is the same or adds up to the signal coming from the second qubit, and without me revealing what the first qubit and the second qubit are, whether they're 0 or 1. Okay, so a circuit to measure, and you probably have seen this, you also see it in these experimental papers. So let's imagine I have qubit 1 and 2, and I'm going to measure Z1, Z2. So I've taken ancilla Okay, if I'm not using enough space here. Let me just, sorry, I'm going to erase this. Okay, so, sorry. Mx. Okay, so this circuit, so I have taken ancilla, I prepared in the plus state, uniform superposition of 0 and 1. And then I have C phase gate, so this gate you are not sure where you're familiar with. So this is C phase or control Z. As a matrix is 1, 1, 1, minus 1, and all zeros here. And then I do that. I do this 2-qubit gate and that 2-qubit gate, and then I measure the ancilla, and I don't measure it whether, I don't ask it whether it's 0 or 1, but I ask it whether it's plus or minus. So I measure it in the rotated basis. So you can do this measurement by first doing a Hadamard gate or a pi/2 pulse, and then measure it in the 0 or 1 basis. So that's a little circuit that measures Z1, Z2, and you also need to do that for Z2, Z3. And then you look at the outcomes, and when they're both 1, you say, okay, we're still in the code space. But clearly when Z1, Z2 is minus 1, and this is plus 1, we have an error, an X error, a bit flip error on the first qubit, right? Because a single error, so there's two ways of seeing this. I mean, I think for here, clearly you see that if you have a single bit flip error, it changes the parities. So you'll detect it if you look at parities, yeah? A more formal way of seeing this describing this, which also applies if I talk more generally, I can say, well, I have a single bit flip error on qubit I being 1 to 3, and this will anti-commute, so Z1, Z2. So it is minus when I is 1 or 2 and plus when I is 3. So polys have the nice property that they commute or they anti-commute. So these guys commute or anti-commute, and so when they anti-commute, so let me write this down because it's also a fairly trivial relation, but it's very useful to understand this. So let's imagine I have an error. Okay, so I'm going to do this more generally, otherwise it's maybe too trivial. Okay, so I'm noting here that the errors that I want to detect and correct all anti-commute with the checks that I'm measuring, right? And that implies that if that error happens, my check will have, instead of plus 1 eigenvalue, have minus 1 eigenvalue. So let's just show that explicitly. Okay, so I have my code word, and let's imagine an error happens. An error happens, it's just some poly that happens. And let's call this P for parity check. P is a parity check. I'm not specifying what it is. It's maybe a product of some Z's, a product of some Y's. And what does it mean to measure this parity check? I determine what its eigenvalue is. Yeah? So I said polys, this is a product of polys, this is some poly, and polys either commute or anti-commute. Yeah? Now, so two cases. There is case when they commute. Then I just have, this is equal to EP psi. And this is my parity check on a code word. And the code space is defined as all the states that satisfy the parity checks, meaning they all have plus 1 eigenvalue. So this is E on psi. Yeah. So if they commute, I see that the state with the error is in plus 1 eigenvalue state with respect to the parity check P. Yeah? So meaning that if that error happens, and I measure this, this guy is not going to reveal it. This guy is not going to tell me that the error happened, because its eigenvalue is still +1. Okay, other choice, the anti-commute. So then I get a minus sign, minus E p psi. And again, p psi is the code word, so it is minus E. Yeah? So now what I see is that the parity check has eigenvalue -1 with respect to the code word with the error on it. So then the parity check will reveal that the error happened. Yeah, so the picture now is that the errors, they will, okay, so I'll come to that in a moment. Maybe so typically what the errors will do that you want to correct, there must be some parity check. There must be some parity check that reveals that error, right? There's two things that have to happen. An error has to be detected, meaning some parity checks have to come out to have -1 instead of +1. And of course, you have to be able to correct it properly. Yeah, so that's two different things, two different conditions. But this is it means that the errors that you want detected, they should be anti-commuting with the parity checks of the code. Okay. So what were we doing? We were writing down the circuit to measure Z1, Z2. And that's a pretty simple circuit, and there's a similar circuit for Z2, Z3, of course. Now, if I want to specify a code, so if I want to specify a stabilizer code, I can do this very concisely. So yesterday I said a code is just some subspace in a large dimensional space. And typically these code words, not in this case, but typically these are very highly entangled vectors. So the description of my code may come out to be very awkward. Yeah? For stabilizer codes, this is not the case. Yeah? For codes which are defined by these type of parity checks, I can define the code space as, well, the +1 eigenspace of the parity checks. But now there are other properties. Namely, I want to say, what is my logical operator? And I already mentioned this yesterday. So let's erase this. Okay, so I select two states which are my logical 0 and logical 1. And now there is a logical operator that maps these guys onto each other. So in this case, I have to flip all the bits to go from 0 to 1. And then there's also a logical z. Now, how is the logical z defined? It maps the logical plus onto logical minus, or you could also define it, it just has to be an operator, a product of Pauli's, which has this state as a -1 eigenvalue state, and that state is a +1 eigenvalue state. Because that's how a Pauli z happens. So I could choose that as z1, but also z2, or z3. So this is an important point. What it means is that the logical operators are not uniquely defined. Why not? Well, let's take a code word. So the logical operators are defined by what they do on a code word. Yeah? Let's take the logical z. Let's take this logical z1. But I could always multiply this by a parity check. Why can I multiply this by a parity check? Because the parity check has this as a +1 eigenstate, so it acts trivially. It doesn't change that state. Yeah? So if I do that, I get z1 twice, so this is z2 side. Yeah, so a logical operator is not unique. It can be multiplied by these parity checks because these parity checks act trivially on the code word. They don't change it. So their action on the code space is the same. That their action on other states is different, we don't care about. Now you see that this repetition code has, why is this a classical code? Well, because you can correct one bit flip error, but you cannot correct any phase flip errors. Yeah? So now, in order to discuss the stabilizer code, we assume that we have errors, x, y, or z, and y is just the product of an x and z errors. We have such errors happening on some qubits of my code word. And we want to say, well, can a code correct single qubit errors on any of the qubits? Huh? Or can it detect single qubit errors? Okay, so now why can the code not correct any phase errors? So z errors. Well, a z error on a single qubit. So let's imagine I have this state. Error on z1 happens, and then I get this state. It still satisfies the parity checks, right? Because it's just a limit combination of 0 and 1. So from that you also see that so how do I find, I can find these logical operators by just seeing what their action is and just guessing what it is. But they do satisfy some special properties, namely that x and z commute with all parity checks. I mean, I'm quite loosely talking about parity checks. Sometimes say they're just stabilizer elements and so on, but I'm calling them parity checks. Well, why do they commute with all parity checks? Well, of course, because if I had a code word and I applied x, I better still be in the code space, right? So if I apply my p and I say, well, these guys either commute or anti-commute. If they anti-commute, that p has -1 eigenvalue, so I'm outside the code space. Yeah? So they have to commute. Yeah, so the problem is with this code, it's not at all protected against dephasing, right? Which is more clear, it's a classical code. And the way you see that from code prescription is just say, well, the logical z is weight 1, meaning it acts on 1 qubit, and when that 1 qubit, dephases sufficiently much, then I have no protection against it. I cannot detect whether the z error happened with my parity checks. Yeah. Okay. So now, yes, so I'll give you a few properties. Okay, so what is, okay, let me see whether I want to, yeah. Okay, so what does this code do? Okay, but, okay, so what do we get in practice, right? Let's imagine I just have bit flip errors. And originally, if I have a bit here, with probability p, it undergoes this bit flip error. Now I have 3 bits. I made things worse. Because now there can be an error there, or there. So that's an error rate of, probability 3p. Yeah. But the point is that if one of those qubits undergoes an error, and assuming now I can measure these guys perfectly, I can correct this error. So that's fine. But what if 2 errors happen? I cannot correct this, right? Because if these 2 bits flip, I'll conclude that this bit actually flipped. So let's write this formally. Because again, it demonstrates a very simple thing. Okay, so let's imagine x1, x2 happened. So this is what I call E real, And I'm assuming, you know, this, of course, the probability that there are two, these 2 bits have an x error goes like p squared, right? So I'm, you know, because I'm assuming that every qubit has independent noise, this happens with lower probability. Okay, but let's say it happened, but I'm assuming that only single qubit errors happen. So if this happens, my Z1, Z2 it still has +1 eigenvalue, but my Z2, Z3 has -1 eigenvalue. Because it anti-commutes with this guy. And of course, assuming that a single qubit error happened, I would say, because of the other parity check, I'd say, you know, E that I infer is x3. So I'm guessing x3 happened. Yeah? And you know, I've learned about feedback, so I'm now applying x3 on my code word to correct the error. So what happened in total? E real, E infer. That happened in total. That's x1, x2, x3. Hey, and that's a logical x. So I've actually flipped my logical information without knowing this. So that's bad, right? Now that's, in this case, very simple. But this is the general principle behind error correction for any of these Stabler-Kaiser codes in the following sense. So some real errors happen, and I have an algorithm by which I infer what errors I think happened based on my parity checks. This algorithm may take into account information, what is likely to happen and not, my noise model, of which I'd like to have a very accurate description so I can make the best inference, right? Now, there are 2 situations that can happen. One is this type of situation, is the bad situation, namely that the real error happened times the error that I inferred is a logical error. And the other situation is, maybe I will elaborate that. I'll come to this a little bit more formally in a moment, so I'll repeat it. I'll tell you, there are only 2 situations, assuming that I can measure my parity checks perfectly. So let's assume I measure the parity checks perfectly. I claim there's only 2 situations. I can give you the argument for that in a moment. Either the error that I infer times the real error is proportional to a logical operation, in which I say, you know, in which I've done a bad job at correcting the error, or the inferred error times the real error is proportional to a parity check. And, you know, these parity checks act trivially on the code space. So they don't do anything with my data, so I'm fine. So this is good. So if you do any numerical studies of error correction codes in terms of estimating a threshold, you let some real errors happen. Well, you have set up some Monte Carlo simulation, which you sprinkle errors on the qubits with a certain, according to some noise model, and then you have your algorithm, your decoding algorithm, as it's called, infer some errors, and you look at whether you're in this case, on that case, and with what number events you end up with this, and what number events you end up with this, and that gives you a logical error rate. Yeah? And so you have, say, n events, and out of those n tries, n bad ran into this problem. So then you say you estimate your logical error rate as this. Now, so from this picture, it's sort of clear that the logical error. So if you use a code like this one for bit flip errors, I said, if I have single errors happening that will occur with probability p, I can correct them. So in order to have a logical error, I need 2 errors like this. So what has been the advantage of the code is that a basic error rate of order p gets mapped onto a logical error rate which scales like a constant times p squared. Yeah, this is not so clear in this board. And this is the general, so that's for this bit flip code that corrects one error. But this is the general principle. Yeah, so if your code, say, can correct 10 errors, let's say I have a code that is, well, maybe I should take an example. So, well, I don't want to take an example. Okay, I'll come back to this later. Perhaps this is better. Of course, maybe I can say this right now. This logical error rate scales like a constant times p squared, because you have to fill in some details about how many possible ways can these errors happen, right? You know, it's 3 choose 2 and so on. So for error correction to help, you like this probability to be lower than your error probability to begin with, which is not true for general p, but we'll come back to this. It's only true when p is sufficiently low. So that's what's called a threshold. Okay, so now I want to talk a little bit about what we do when our parity checks are noisy. Yeah, so I wrote here, which I erased, a circuit to measure these two operators. It used some C phase gates and it had an ancilla. And one can assume that the components in this circuit are also inaccurate. Yeah? So we're not getting the eigenvalue of this operator accurately. And of course, we're not also getting it as just, a value that's 0, 1. We're getting some noisy signal that we average over time, and that we then bin and identify this or 0 and 1. So we assume that there is some error with which you get this information. There's several different strategies, and if you want to know the difference between topological codes and the more and concatenated codes, it relies partially in what you do when such components are noisy. So one option, and we'll look at that for the repetition code, is to repeat and not take every bit. And not take every parity bit seriously. These parity bits are also called syndromes, so sometimes I'll call them syndromes. Okay, so now let's imagine instead of having 3 bits, we have n bits, and they're on the line. And n is 7, and in order to, so I have this 7, this is my codes, and these parity checks are now checking the parity of these neighboring bits. Yeah? So I want to also use some color. So everywhere in between these, I'm noting that, so these 2 bits I have to check the parity of, so I put an ancilla here, and in the experiment it's really done like this. Put an ancilla here, I do these 2 C phase gate, I measure the ancilla, and then I get an eigenvalue +1 or -1. Yeah? And so the first thing to note is, let's imagine I get this pattern. Okay, so let's first do this when the parity checks are still reliable. So the green thing denotes that it's -1, oops, and this is +1. Okay, so now let's think about it. This parity check comes out to be -1. That can be due to an error here or there, right? If the error is here, then this parity check will also come out to be -1. Yeah? So that's a possible way of explaining these 2 dots. Similar, I have something here. I could make this array a little longer. Sorry, I just have to. Let's make it a little longer. Sorry, everybody was drawing this and I'm already changing it. So let's look at this. So here I have a parity check that came out to be -1. So again, in this qubit or that qubit, there could be an error. Now, let's imagine there's an error on this qubit and that qubit. What does that do? Well, it doesn't change, then the parity check here is +1, right? Because here, if I have an x, that commutes with zz. X commutes with zz. Twice an error is no error, so to say. So, and again, if I would continue here, if I would have error here, that again would indeed point to having no, +1 parity check here. So, point is that if I want to determine an error for this family of parity checks, I just need to connect them up in pairs. Oops, sorry, like this. That's one way of connecting them up. But another possible interpretation of what I have here, too many dots. Okay, so I have this. See, the thing is that this works, let's see, this. Another possible thing is to say, oh, okay, there are x errors here, so I connect these up, and then there was an x error there, right? Because a single x error there, that would have made this parity check to be -1. And there was a single x error there. So this could be matched to the boundary, so to say. So that's another possible error that could have caused these parity checks. So how do I decide? So the two in this string, there are two possible errors that could be responsible for the parity checks. Now, how do I decide which one to choose? Well, I'm assuming that errors are not too likely. So an error pattern that acts on more qubits is less likely than an error pattern that acts on few qubits. So what I need to do is I need to choose the pattern that acts on the fewest qubits. So here that's x, and then these 3, so that's 4. And here, well, problem is here is also 4. Okay, bad case. Okay, so this is 2. Well, this is not so, this is a good case because it indeed says that the 7-qubit repetition code cannot correct 4 errors because it has this ambiguity. So it could correct 3 errors, then it would still be unique which one has the lower weight. I would have to make this a bit longer to decide this. Okay, so the error correction takes place by doing some kind of, in a very trivial form, minimum weight matching. Now what I mean, this is the sort of baby version of what one does for the surface code. And one says, okay, so I have this pattern of defects or places where the parity checks are non-trivial. In one of the papers, they call them detection events. And I have to pair them up via a chain of errors, because a chain of errors can cause such pattern. And I want to minimize the weight of that chain. And in this case, this is very simple. I don't really need to do any complicated math. I just, have to choose between these two patterns, and one has less weight than the other, assuming that the number of errors is small enough. Okay, so now what happens if your parity checks are noisy? So if your parity checks are noisy, so the way we deal with that for the repetition code, or can deal with it, is by repeating these parity checks. So instead of getting the parity checks once, I just keep getting them as often as I can, just keep repeating the circuit and see what happens. So now I have a time direction, and this is a space direction. And it could, for example, happen that here I have let's see, this happens. I have something patterned like this. Here everybody is good. We're still in the, it looks like we're still in the code space. And then this parity check lights up. And maybe it lights up another time and then it's gone. So then you say, well, how should I interpret this? So the way we can deal with this is saying, well, it's more likely, so now the parity checks are noisy. So I should also, instead of only having errors on the qubits, I can also have errors on the parity checks. So I'm going to now note, so here, from here to here, the parity check changes, right? So I'm going to put a cross here. Now here it stays the same, and here it changes again. So, and here it's it also changes, and this also changes. And now, so in 2 dimensions, I was also, well, I wasn't looking at where it changes, I just looked where it was lighting up. But I was pairing these things up. Now what you do now, in if you also include time, you're saying, I'm going to match, for example, this way. I'm going to, so because the fact that it changes and then it stops is possibly due to, these 2 checks being noisy. So it's kind of like doing the repetition code in this time direction. You're just repeating. Okay, so let me show this. This is actually from a paper with topological quantum memory by Dennis et al., in which they discussed this for the surface code. But this paper I can use very easily for the repetition code. So in this picture, I have qubits on horizontal links. And the measurements are on the vertical links. And where they are gray, a little fat, they come out to be -1. And when they're not fat and gray, they're +1. And so I can look at such a pattern, and I can say there are errors which have the space-time character. So the errors that are horizontal, which are just errors on qubits, and the errors that are vertical, which are errors on my parity check measurement. For example, this guy over here, this parity check came out to be -1, and it could be just due to that parity check being bad, right? So I'd say that's an error, a vertical error. And but there are also qubit errors. For example, these two parity checks, they were +1 here, but then they're -1 together, onwards. So that could be because there was a qubit error here, and that was not corrected. That was just a qubit error that happened here. Yeah? So that's this black line. And now let's put red dots on this figure. And where I put the red dots is just where the values of these parity checks change. So for example, here it was in this line it was all +1, it switched to -1. So I put a red dot here and I put a red dot there. And again, a red dot there, there. So here I've put a few of these dots. And the algorithm to decode, to determine a likely error, is we just match up pairs of dots via minimal length black segments. This is, very roughly, because if we choose the minimal length error segments, so these are error segments, maybe, it depends on whether the probability for error for my parity check measurement is higher or lower than my probability for a qubit error, how I should optimally pair these up. So I use information about my error model to try to optimally decode this. Okay, so maybe this, I don't know whether this sort of sinks in, but let's now, so what is nice is that actually in a very recent work, which I think come out in Nature, partially in the, so there's recent papers by the Martinez group. This is UCSB, Google. And also by the DiCarlo group in Delft on doing this kind of repetition code. So let me say something about this. So so I don't know if you can see this so well. Okay, so this is a slide showing the chip of this Martinez experiment, which is on Xmon qubits, which is a variant of the transmon qubit. And so such a qubit, an Xmon, is here's denoted by this cross. So it's a piece of superconductor with a capacitance and some Josephson junction. And you see these are fairly close and they're very directly coupled. So when these are brought into the right resonance condition, you can do 2-qubit gates here between nearest neighbor Xmon qubits. There are lines here, they are flux lines. I think actually, I can say a few things about this, but probably in the Delft school you hear much more about this, because of course DiCarlo can tell you about this experiment. There are flux lines here that control the resonant frequency of the qubit, by which you can turn it in and off resonant with what you like to do, as you can kind of take it offline when you need to. And these are 9 qubits, and you see that actually there are 5 data qubits. So in this experiment, they could do a 5-bit repetition code. And these green guys are my ancilla for my 2-qubit parity check. Yeah, so they do a little circuit. So you see here, this is the circuit for a 3-bit repetition code. So I have 3 data qubits, and I have 2 ancillas for Z1, Z2, and Z2, Z3. And you see the circuit, well, it doesn't use C phase, but it is sort of a version of it. There's just two of these C naughts happening in order to measure, I don't know if you can read this, Z1, Z2, and Z2, Z3. And here, so in this experiment, they have also readout resonators that are sitting, that every Xmon or every qubit has to read out the state. And what they do, what is nice about this experiment is they do 8 cycles of error correction. So they assume that these parity checks are indeed noisy, and they repeat, just like what I said this. And they actually, there's, in the appendix of this paper, they show how they try to optimally decode this with all the information about the error model that they have, including some leakage. And they try to infer the errors the best they can based on all this noise information. So what I like, why do I bring this up? Because I think it shows that, this type of, this at least the repetition code is not, and what I'm describing here in fairly mathematical terms, is not at all far from any experiment yet.
So what is the how's it implemented here?
That's done by a C phase.
Yeah, but how's it physically implemented?
So they change the resonant frequency of, let's say, one of these qubits gradually, and they go back. So, yeah.
So you tune it in on the phase.
Yeah, but it uses a higher level also. So, I mean, it's a complicated description of the gate. I don't think I can summarize this. It's not just bringing them into, I don't think I mean, there's many more, I don't think I'm going to go into the details of this. It takes about 10 nanoseconds. It's a fairly, fast gate. And they've demonstrated this gate in another setup, which would have very, very high reliability, over 99%.
But they have to do them all at the same moment?
No. So they split that. No, because you cannot. They do them, I think there is some timing of these things. Of course, you'd like to use the minimum amount of time to collect all parity checks, but they have to do it such that, there's these neighbors, and you don't want, if, this guy is off resonant with these guys when they talk to each other. So you say, okay, I tune these guys close to each other, and this guy is off, and then I can't use it for that moment in time, but I can use the next pair of qubits to do something. So they have a scheme in which they, how do you say, they try to minimize the total amount of time they use but they cannot do it all simultaneously, there are, I don't have this here, but the supplementary material has many of these details. Yes?
Would it be in general possible to use insular qubits for X and Z parity measurements, like one after another, for example?
Yes, in principle. Of course, the circuit is slightly different. But the thing is that the whole layout has to be changed. If you know, for the repetition code, you only do the Z parity. There's only the Z parity checks. And if you want to do the surface code, you have to go to 2 dimensions and the whole, you know.
That's what I'm asking. If I have just one single line and I could do all the X parity measurements.
Yeah, but I mean, you don't have to, you know, the problem with this setup is that these qubits, they only talk to their neighbors. You know, again, I can discuss this in a moment. You know, I'm not the experimenter, so maybe I should leave that to Di Carlo. But there is, the problem is, okay, so in this thing, it's nice to do the repetition code. But you imagine, you know, if you know the surface code, you know there's something they have to change about this. Because here, if they want to capacity couple these X-mons, nearest neighbor, in 2D, these guys this has to go away somewhere. This has to go up above. And there's also flux lines. This maybe there's another way of doing this. But it's harder, much harder to do this probably in fully 2 dimensions for a surface code.
That's what I'm asking.
Yeah. But I mean, so my point is that if you want to do X checks, the problem is you're going to have to do X checks between this guy, and there's in this layout no means to do this. Right? Because I have to do a 2-qubit gate between this qubit and that qubit. How am I going to do that? I need what I have here, for example, there's a bus resonator. I have a more long-range connection.
I think
No.
my question
Okay.
is, do I really have to do 2D?
Yes and no. I mean, there are codes. There are fault tolerance, and I was going to say this later in my talk. There are codes that work purely in 1D. It's proved by Gottesman, and we have a 2D layout, but the threshold is very bad. If you use concatenated codes, in principle, you can do it in 1D. I mean, what you call 1D is, you know, fat 1D. It's not like a single line of qubits, right? So you actually don't need to go to, you know, 2 or 3, but the threshold of these constructions is bad. Okay. Now this is the chip of Martinez, and in their experiment. So what is nice here is they do this repeated error detection, and they try to process this record in its entirety, which I think is a novel thing. What I'm not so sure about is that it convincingly shows that the repetition code is functioning here. I mean, one question I actually have, and this is actually not at all hard to do, and nobody's done this, is what is actually the noise threshold of this scheme? So I could take, and maybe Austin Fowler, who's worked on this paper, knows this. So you look at your gates. They have a very accurate description of their gates. And let's take n very large. This is a repetition code. So we take the number of bits n large. And you can ask for what basic error rates on my qubits, on my gates, do I get a logical error rate that goes to 0 for large n? Now, the problem is, of course, that these error rates is not just one error rate that goes, because you have a complicated noise model that holds for everything. But you can ask, what is the noise threshold of this 1D repetition code implemented in this type of way? And I find it actually surprising that I don't, well, maybe it's, I don't know, it's surprising that I don't know it, but I don't think this is actually widely known. Because there have been, of course, results on repetition codes like this von Neumann work, but they assume perhaps, you know, that you take majority values. And here you actually do some controlled NOT gates for which you can put in an error probability. And then you ask, what is the, so if I assume that every gate has a certain probability of error and measurement and preparation, for what probability of error am I below a threshold? Do I get a logical error rate going to 0? And it would be nice to know this number, because it would, and I think it would also be nice to know, before you go to the surface code, that one can do the 1D repetition code. No? I mean, isn't that a more feasible goal before we move on to the surface code? It's not as, you know, it's not as exciting perhaps, but it would be, if we can't even do that, I mean, surface code is much harder, right? Or at least it's likely to have a worse threshold, and it's also harder to realize it because of the 2D character of this, to have this 2D connectivity. So in this setup, they focused more on characterizing the quality of their parity checks. So they just have, they do a 3-bit repetition code, but with 2 ancillas. So I have, these structures are the transmon. So this is transmon 1, or transmon top, transmon middle, transmon bottom. And there are 2 ancillas here. This is hard to read. So every transmon qubit has also a readout resonator, and they're coupled via bus resonators. So the qubits can talk to each other via a bus resonator. So the way to do gates here is different from this very direct coupling. And these are also flux lines to tune the frequency of the qubit, and then there is a input and output line to measure all the qubits. And so then this type of thing also is sort of an experimental version of the type of circuits that I showed here. Okay, so what do we want to do next? Are there questions on this? So, okay. I wanted to talk about amplitude damping. Okay, I'm not going to do this yet. Let me just think about it, whether I want to do that or want to just move on. It may confuse you. Okay, I want to say something about amplitude damping here, because that was the original plan. Okay, so I want to give you another example of a code which is more quantum than the repetition code. So the point about, if you go to quantum codes, 3 bits is not enough. We just saw that. 4 qubits is also not enough, but you can do something. So the smallest code, quantum code that can correct a single qubit error is a 5-qubit code. But it's not particularly pretty, or at least it doesn't have very nice, it's a stabilizer code, but it doesn't have very nice other properties in terms of its noise threshold and so on. After the 5-qubit code, you have the 7-qubit code, which is also called Steen's code. It's the smallest color code, and there's been an experiment in the blood group on ion traps realizing this. And then we have the 9-qubit code, which is a SOR code, which one obtains by concatenation. And that is also can be viewed as the smallest example of the Bacon-Shor code family. So that's a bit about small codes. But I want to talk about what we can do with 4 qubits. Because if they do a 3-qubit experiment, maybe the next experiment will be a 4-qubit experiment. Who knows? Okay, so amplitude damping. So so the idea is that, let's imagine I have a bunch of qubits, and my dephasing is, I want to, the dominant source of noise is amplitude damping due to T1, and maybe, well, first there's also dephasing, but let's imagine I only want to correct for that. Then it turns out one can use 4 qubits to approximately correct this amplitude damping error. And the code words in this case Now, these two code words, what we want to show, or what I'm not explicitly going to show, but what the way one should analyze it is say, okay, I got this two-dimensional subspace, and I have my error operators, and now I'm going to check to what extent the error correction conditions are fulfilled. But you can also see this code space actually as a stabilizer code. So what are the parity checks that have +1 eigenvalue with respect to these two states? Well, I note that the operator x1, x2, x3, x4, we are a +1 eigenstate of this operator, right? Which flips all the bits. So it flips all the bits, so it doesn't change that. In addition, we have, these are always even parity, z1, z2, and z1, z2, z3, z4. And of course, if I say parity check, so if I'm an I'm a +1 eigenvalue of these operators, I'm also a +1 eigenvalue of the product of these operators. So I could associate, I say these are the generators of a group. Yeah. And these operators, of course, all commute because they have to have eigenstates, common eigenstates, common +1 eigenstates. So this is actually an example of a stabilizer group generated by these parity checks. Now I can also note that for these two code words, the logical x is x1, x2, and the logical z is z1, z3. For example, like I said before, these are not necessarily unique operators because we can multiply them with these operators. So another incarnation of the logical x is x3, x4, because I can multiply that operator with this there, and I get x3, x4. Now you note that these have both weight 2, and by multiplying with any of them, they stay actually weight 2. And this implies, so I think I didn't mention, so in general a code, a stabilizer code, I can actually characterize by 3 parameters. I write it like this, nkd. D is the distance of the code. N is the number of physical qubits. And K is the number of logical qubits. Oh, barely. I'm sort of going, or maybe I was going to say this later, but I'm saying it now anyhow. What is the distance of a code? Well, we saw it's the distance is the minimum weight of any logical operator. Why minimum? Well, I got more than one logical operator, so I have to minimize over which all the logical operators I can take. And also, logic operators are not unique. So if I multiply them with some elements here, I have to take the one that's minimum weight. And that weight is the distance. So in this case, the weight is 2. For my repetition code, the weight was 1 because I had a logical z that had weight 1. Yep. And now I can also write a code which can, with distance, let's see, with distance d can detect e-1 errors. Okay, we're talking here about stabilizer code, qubit or stabilizer code, because I'm only good. And, okay, so why, so I want to say this now. Okay, I'm trying to do too many things at a time. Let's leave that for now. So a code generally is written down like this. I encode k qubits, k logical qubits into n. Here, for this case, n is 4, and k is 1. Yeah? And that code has a distance. Now, why a stabilizer code, why can a stabilizer code with this and n's, can it detect any, d minus n Pauli errors? We're only talking about Pauli errors. Okay, so that is actually fairly straightforward to see. in the following way. So when can you detect an error? It's when the error anti-commutes with some parity check. True? Did I already said that? What's the distance of a code? That's the minimum weight of these logical operators. What is the property that logical operators have? Well, they commute. Yeah? So if you look at the structure, so there is maybe I have a picture here. Yeah. Yes. I have a picture here. So this blue thing is a space of all polys, products of polys. The red thing are the parity checks. So that's the subset of them. And now there are operators that commute with parity checks, but they're not parity checks themselves. These are the logical operators. They're not parity checks because they have a non-trivial action on the code space. And the errors that you can detect, they're not in this. They should be anti-commuting. So yeah, maybe I'm not saying this so clearly. Okay, so so the point is that I'll say it roughly. You can check the error correction. There's a more rigorous way of showing this. The point is that if you look at poly operators which are not proportional to parity checks, you look at the low weight ones, well, they cannot be logicals, right? Because the minimum weight of a logical is D, right? So all the low weight operators, they have to anti-commute with some parity checks. Right? Because if they commute with all the parity checks, they're logicals. And they can't be logicals because the minimum weight logical has weight D. Yeah? So that's the argument. So up to D minus 1, there are all these operators, they will anti-commute with some parity checks. Because if they don't, they were logicals and the distance would not be D. Okay? So that's roughly the argument. So that's nice. A code with this and these can detect D minus 1 errors.
Excuse me.
Yes.
Could you please repeat the definition of weight of operator?
Okay. A weight. So we're only talking about polys, right? I'm only talking about I have n qubits and I have polys. You know what I mean by polys? Yes. Okay. So the weight of an operator is just the number of qubits it acts on. So if I say I have x1, x3, z5. The weight is 3 because it acts on 3 qubits. Of course, it acts like the identity on all the other qubits, but I'm not including that. Yeah? Yeah, so the assumption underlying this whole scheme of error correction using stabilizer codes is that it's unlikely that errors on many qubits happen. And so if you'd have very correlated errors, then this would be maybe problematic, right? Because what you want is something that the probability that 1 qubit undergoes an error scales with p, and the probability that 2 qubits undergo error scales with p squared, and the probability that k qubits undergo an error scales with p to the k. So if I have... So if a code which has high distance means that the logical operator acts on many qubits, it means that it's unlikely that logical operator would spontaneously happen, right? Right? Because it has to act on many qubits. Now here you see the logical operators act on 2 qubits. So with that thing, the code can detect 1 error. I may be starting to confuse you now, but anyhow. Okay, so there is a 4-qubit code can correct 1 error. I was actually talking about amplitude damping, so this is why it's confusing. So this code can also correct an amplitude damping error. So if I say this code can correct one Pauli error, I should say more properly. Okay. So I'll say, okay, I don't want to say too much about this amplitude damping because I'm worried that I'm going to confuse you in this. Also running out of time. So I want to show to you why, or how you can see that this code can correct an amplitude damping error. Now, there are two error operators, A0 and A1. Well, you see that A0 is close to the identity plus order gamma. That's 1 plus order. And A1 is the error that happens. So what I could look at, I could say, well, assume that I have a set of errors which says that AI square root of, this is sigma minus on qubit. So this is the operator, this is sigma minus. But now I imagine I have 4 qubits, and any of these 4 qubits could have undergone some amplitude damping. So 1 would be mapped onto 0. And so there's 4 errors, and the other qubits just nothing happens with them. And I have also the, nothing happens. So the claim is that this set of errors satisfies the QEC conditions. Remember the QEC conditions, I specify a bunch of operators, and I just need to verify whether this certain equality is obeyed on this code space, right? So I have P, AI dagger, AJ, P is this alpha IJ, P. But intuitively it meant that these errors, they send the code space to orthogonal spaces. Now, if I have this error, the identity, we just stay in the code space, nothing happens. So I want to understand if I have one of these errors, so only one qubit undergoes this, its state is changed from 0 to 1, that's what's happening, whether I indeed obtain orthogonal states. So let's check that. Let's imagine that I have A1 on 0 or A1 on 1. What happens? Well, A1, the qubit 1 has to be a 1 to start with, right? Because this is sigma minus, so state 1 is mapped onto 0. So if I apply it on 0, there's no contribution coming from here, and this bit gets mapped onto with the square root of gamma, but that's not so important. And now for the other one, I similarly have this guy. Now, so I said there is, okay, so maybe I should show you what A2 does to, so one could go through, A1, A2, A3, A4, but let's see what A2 does. So A2 gets you, this. Yeah, so the second qubit. And it's sort of clear that, I don't know, maybe clear that so these two states, these are just bit strings, they're orthogonal to these two states. And again, if I apply A3, I get two 4-bit strings that are orthogonal to these two pairs. And A4 is another set of 4. Now, if I want to do error correction, I should not distinguish between those guys, of course. Right? Because if I just say, well, I'm going to measure whether I have this state, then it would also tell me that it actually came from the logical 0. So I've gained too much information. So one way to think about this is to say, well, these two states have again there's some parity check operators that have +1 eigenvalue for this. For example, Z3, Z4 is +1, Z1 is +1, and Z1, Z2 was actually -1. That is defining this pair of states. One has to check that there are not more states that have this property. One can do this simply. So in principle, you could say, oh, I could measure these. So there is a procedure by which you actually determine in which of those subspaces you are, right? So there are kind of 5 situations. One is there's nothing happened or an amplitude damping happened. And what we know is that we are in orthogonal subspaces. But of course, what measurement we have to do to determine which subspace we are may not be trivial. So I'm actually currently doing a project with a postdoc in which we try to do this measurement in a very direct way, which we believe is actually not, wouldn't require a whole big circuit of qubits. Maybe not so hard in a particular hardware that we're considering.
Excuse me.
Yes.
The application how you apply the error operator A1 and A2 to the logical state, right?
This is what happens. This is not what I want to have happen, right? This happens.
But I'm confused if you compare to the definition of a logical state, which is a superposition state. Right?
Yes. So what happens with this? Okay. So what happens with this amplitude damping noise is that you get from the superposition state, you get a single state. Why? Because if you started out in 0, 0, 0, and you apply this operator, it annihilates, right?
But it should affect only one of
so it affects
only one of the physical qubits, but not all of them, right? So
no. Yeah, but it's the identity in all this. So we assume this A1 is on qubit 1, it's A1, and qubit 2, it's the identity. Do nothing.
Yeah, so all the qubits should be still in a superposition state.
No, but I mean, it's just the product of these operators, right? I just say it's A1, tensor, identity on qubit 2, identity on qubit 3, identity on qubit 4. And if I apply that to the state 0, 0, 0, it's A1 on 0, tensor, identity on 0, tensor, those don't change. But so this is 0. This is just like an annihilation operator, right? So, okay. So the point, what this amplitude damping does is not a Pauli error. A Pauli error would just be, a unitary rotation, and it does map this onto different states. So what it means, which is not so nice about this code and more general amplitude damping code, is that the recovery. Let's say I've determined that I had this amplitude damping error. Then I'd like to undo the error. In order to undo that, I have to take these 2 states and make a little circuit that maps these back onto these. And that circuit is not just a single Pauli somewhere, right? It's more complicated because I have to create entanglement out of a product state. You're still looking puzzled. Yeah, maybe you can discuss it after the. Okay. So, so I just want to finish this. Okay, so the argument is that if this were the set of error operators, they would send the code words to 5 orthogonal subspaces. Well, the original subspace of 4 error spaces. And I could, in principle, detect that and correct it, because these are orthogonal spaces. But this is, of course, not quite what we have, because if we have these 2 error operators, and this is close to the identity, but not quite. So you have to change this. I mean, first of all, there's also corrections to this. You have to, develop this in orders of gamma. And in particular, you have to change the identity 4 times into having A0 4 times, which is kind of the no error case. And so you can see what happens. So my point is a little bit like if no error happens, it still changes the code states. And so it's still an error. But no, not at the error that you may want to focus on. So I have A0 tensor 4 on 0. Well, what does A0 do on every qubit? It just changes the weight between, it maps 0 onto 0 and 1 onto square root of 1 minus gamma 1. So I get some prefactors, right? Because I change the weight then of this state. And I have 4 times that factor. So that becomes and I have similar prefactor of 1 minus gamma. Let me just check that I'm not. Yes. Now, so this is the no error event. What happened with this guy? Well, there's just some prefactor in front, and this is still the old code word, so that's fine. But here you see that this is now, there's a different weighing between the all zeros and the all ones, which means that, unfortunately I just erased it. I said these code words, they were eigenstates of some parity checks, right? And one of them was x1, x2, x3, x4. So this is an eigenstate of x plus 1 eigenstate of that operator, these two. But this is no longer. Because if I apply x1, x2, x3, x4, then this is still an eigenstate, but that's not. And another way of saying that is that actually this, if I expand it in terms of identity and z's, right, which I can do because it's diagonal, there is a little z error in here. And this code can actually, well, in order to detect z errors, you have to measure this. But we cannot correct this z error. 4 qubits is too little. So in that sense, the 4 qubit, this uses the 4 qubit code. It can reduce the rate at which amplitude damping happens at the cost of potentially increasing the dephasing error. And if you want to use, if you say, well, I want to also be able to correct the dephasing error, then you have to concatenate this code. So you have to use this in a more complicated scheme, and I think I'll get to that in the next lecture. Okay, so we're going to stop here now today. Questions? Maybe in the break is also possible. Break. We need to get a break. Okay.